Hello students, so welcome back to the first semester mathematics honors classroom. So we have already started with the second paper, that is 102, and I have started the second unit, which is relations, functions, okay, various types of relations and all. So in the last class I had stopped with Cartesian products. So let us begin from where we stopped, the Cartesian product of two sets. Okay, Cartesian product of sets Okay, so we have, suppose you have two sets A and B, B two non-empty sets, okay, then the Cartesian product of A and B is denoted and defined as A cross B equal to the set of all those ordered pairs where the first element is from the set A and the second element is from the set B. Okay, so this collection of ordered pairs is called the Cartesian product of A and B. Okay, so if A and B any of them is empty, then the Cartesian product itself is empty. Okay, so suppose for example, if I take the set A to be 1, 2 and 3, and I take the set B to be say A comma B comma C, okay, in that case what is the Cartesian product? A cross B will be equal to 1 will be paired with A. Okay, each element of the first set will be paired with each element of the second set. Okay, 1 will also be paired with B, 1 will be paired with C, okay, and then 2 will be paired with A, then 2 will also be paired with B, and then 2 will also be paired with C. Okay, similarly 3 will be paired with A, then 3 will also be paired with B, and 3 will also be paired with C. Okay, so the Cartesian product A cross B will contain exactly these elements. Okay, and the Cartesian product B cross A, it will contain the elements same A. So the first element will come from B now. Okay, the first element will come from the set B. So A will be paired with 1, A will be paired with 2, A will be paired with 3. Okay, then B will be paired with 1, B will be paired with 2, and then B will also be paired with 3. Okay, and then C will be paired with 1, C will be paired with 2, and then C will also be paired with 3. Okay, so this is the Cartesian product B cross A. Okay, so from the product itself you can see 1A is an element inside A cross B, but 1A is not inside B cross A. A1 is inside B cross A. Okay, so it is not necessary that A cross B and B cross A will be the same sets. Okay, in fact, whenever A and B are different sets, A cross B will always be unequal or different from B cross A. Okay, so this is one. Next, suppose you have, so that is why these are called actually ordered pairs. The order is important. If one comes first and A comes second, this is different from A coming first and A1 coming second. Okay, so that is why these are called ordered pairs. Okay, so it's this AB, they are actually called ordered pairs. Okay, these are ordered pairs, right? So we have A cross B is the collection of all ordered pairs of elements coming from the first set A and the second set B. Okay, so suppose you have the set A has n elements. Okay, number of elements of A is suppose n, and number of elements of B is suppose m. Okay, then what is the number of elements of A cross B? The number of elements of A cross B will be n multiplied by m. Okay, so it's quite easy to see. Each element of the first set is paired with each element of the second set. Okay, So for each element of the first set we have how many ordered pairs. So number of ordered pairs with an element, with each element of the first set is exactly m. Okay, and there are n elements in the first set, so the number of total number of ordered pairs will be n multiplied with m. Okay, so it's the same for B cross A also. The number of elements in A cross B and B cross A both will be same. Okay, even though the sets will be different, but the number of elements in A cross B and B cross A will be always same. Okay. Then you have suppose if you have the same set A, okay, then also you can define A cross A. So A cross A is the set of all those A comma A, A comma B, such that A comma B both belong to the set A. Okay, so both are coming from the same set. So that means basically when A and B are equal, capital A and capital B, if these two sets are equal, in that case we get the Cartesian product of the set with itself. Okay, so for example, if you take A to be the set 1, 2, 3, so what is A cross A? A cross A will be 1, 1, then 1, 2, then 1, 3, okay, and then 2, 1, 2, 2, then 2, 3, okay, and then 3, 1, 3, 2, and 3, 3. Okay, this is the Cartesian product of A with itself. Okay, so this is one. Next is how can we show this Cartesian product in a diagram. Okay, so for example, we have something like this. For this particular set, say we have a line of this type. Okay, and so this is this represents the y-axis, this represents the x-axis. Okay, so we have suppose I have the set A. Suppose now I have the set A, which is already we have seen, or let us take a different set. A equal to, say I take 1, 2 and say 3, and B I take a different one. Suppose I take 4, 7, 0, okay, or say 8, 4, 7, 8. Okay, suppose I take this, or I take another element here, 4, 7, 8, 3. Okay, 4, 7, 8, 3. Suppose. Okay, so in that case, what we can do is we can designate these points by, say I designate this point by I designate this point by this. So this point is 1, and I designate this as 2, I designate this as 3. Okay, so these are the points of the first set, and I designate the points of the second set here, 1, 2, 3, 4, 5, 6, 7, and there will be another element here, 8. Okay, so just let me just rub these parts. Okay, so these are the points, and suppose I draw this line now. Okay, so let me take it in the black color. Yeah. Okay, suppose this is the line that I have drawn. Okay, and then I designate some points here, A, B, C, D. So here it's 1, 2, 3, 4, 5, 6, 7, and then 8. Okay, so suppose these are the points. So what will be the elements of A cross B? So the first element will be 1, 4. 1 is paired with 4. Okay, so the point will be somewhere here. 1 is paired with 4, 1 is paired with 7. Okay, 1 is paired with 7, then 1 is paired with 8. Okay, 1 is also paired with 8, 1 is paired with 3. Okay, so these elements will be there. then 2 will be paired with 4. Okay, so this elements will be there, then this will be there, this will be there. Okay, each element will be paired with each element of the second set. Okay, so this in diagram we can represent it this way. Okay, the Cartesian product of two sets A and B. Okay, so these points will represent all points in the Cartesian product A cross B. Okay, so this is there. Now let us see what is a relation. Okay, let us see what is a relation. Relation, okay, relation on a set capital A. Okay, or yeah, relation on a set capital A. So a relation on a set capital A is a subset of A cross A. Okay, so any relation on a set A is actually a subset of A cross A. Okay, you take any subset, you get a relation on A cross A. Okay, for example, if I just denote this A as the set, say A comma B, C comma D. Okay, so across A has got actually 16 elements. Now I take a relation R1, say this one. It is relation is a subset of A cross A. So suppose I take this subset, A is related to A, B is paired with B, C is paired with C. Okay, so this is going to be a subset of A cross B. Okay, this is a subset of A cross B. So this is a relation. So R1 is a relation on the set capital A. Okay, R2, suppose I take another relation, A paired with A, then A paired with C, then B paired with C, and B paired with D. Again I take something like D paired with A and D paired with itself. Okay, this is also a relation. This is also a relation on A. Okay, so R2 is also a relation. Then we have something like R3. You take any subset, it's going to be a relation. So if I take a singleton subset, this is also a relation. R4, I take something like A related to C, C related to B, okay, and B is related to D. Okay, so this is also a relation. Okay, so we can have relations of several types. So suppose I have this again, R5, say this is equal to A related to A related to B, then A related to C, okay, A related to D. Okay, so this is also a relation. This is also a relation because it's a subset of A cross B. Sorry, A cross A. This is a relation on A. Okay, so how many relations can be there on a set having n elements? Let us try to answer that question. How many relations can be there on a set having n elements? Okay, how many relations can you define on a set having n elements? Okay, so this is the question. How many relations can we define on a set having n elements? Okay, so what we have seen is any relation is a subset of A cross A. Okay, so suppose the number of elements of A is equal to n. So what will be the number of elements in A cross A? A cross A will have exactly n square elements. Okay, number of elements of A cross A will be n square. So number of relation, we know that every subset of A corresponds to a relation. Okay, so number of relations will be what? Number of relations relations on the set capital A will be equal to the number of subsets of across A, equal to number of subsets of A cross A. Okay, so how many subsets are there of a set having n square elements? So there are exactly 2 to the power n square subsets. Okay, so number of relations on the set A is exactly equal to 2 to the power n square. Okay, if the set A has n elements, then exactly this many relations we can define. Okay, so in this earlier case that we have taken, A is a set having 4 elements. So number of relations that we can define here is number of relations will be exactly equal to 2 to the power 4 square. Okay, so 2 to the power 4 square. Okay, this many relation 2 to the power 4 square. So that's actually a huge number, 2 to the power 16. Okay, 2 to the power 16. This many relations we can define. Okay, so if because across A has got 16 elements, so each subset of across A will give us a relation, right? And there are 2 to the power 16 subsets of across A. Okay, so we can define 2 to the power 16 relation on across A. Okay, so this is the thing, right? So let us see some examples. Okay, before I go to example, I mention another thing. The relation that we define can be between two sets also. Okay, relation from a set to another set. Okay, to another set. Okay, so what is that? A relation from a set capital A to another set capital B is a subset of A cross B. Okay, so a relation on a set was a subset of A cross A. A relation from a set A to another set B is a subset of A cross B. Okay, so for example, suppose A is the set 1 2 5 and B is the set A comma B. Okay, so a relation, suppose I define something like R1 equal to, so 1 is related to A, 1 is related to B, 2 is related to A. Okay, so this defines a relation on X cross B, or this defines a relation from A to B. Okay, suppose I take another relation, something like this. 1 is related to A, 2 is related to B. Okay, and nothing else is related. Okay, then this is also a relation. Okay, I can take another relation as R3 equal to 1 related to A, 1 related to B, then 2 related to A, 2 related to B. Okay, then I can take 5 related to A, 5 related to B. So in fact here I have taken the whole across B as the relation. Okay, because across B is itself a subset of across B. Okay, so this relation also we can take. So there are how many elements? There are 6 elements inside this relation. Okay, any subset of across B is a relation, right? So here we have got this. Next, if we see some more examples, or some types of relation. Okay, types of relation on a non-empty set. So there are several types of relation. In particular, when we consider the case relation on a set A, that is subsets of A cross A. Okay, in that case we'll have several types of relations. Okay, so types of relations. Okay, just before that, you may just recall in higher secondary also we have done what is the domain of this relation. the domain of this relation is, for this relation R1, what is the domain? The domain is the set of all first elements. Okay, so here the first elements are 1, 2. And what is the codomain, or the range of this relation? The range of this relation is actually, the set of second elements. Okay, the elements which are related to some element in A. Okay, right. So the range is this. The codomain is the set AB itself. Okay, means the set B, the second set itself is the codomain. Okay, so that we can understand. So types of relations on a non-empty set. Okay, non-empty. So please remember that empty relation is also a relation. Okay, because empty set is also a subset of every set. So A cross B also, the subset of the empty subset of A cross B, that is also a relation. That's an empty relation. Hence no element is related to any other element. Okay. So let us see some types of relations on a non-empty set. So first is a reflexive relation. Reflexive relation. Okay, a relation say R on a non-empty set, is said to be, on a non-empty set capital A, is said to be reflexive if the ordered pair, this A comma A, this is always an element inside the relation for every A inside A. Okay, for every element of A, capital A, the ordered pair A comma A is inside R. Okay, that means every element is at least related to itself. Okay, such a relation is called a reflexive relation. Okay, a relation R on a non-empty set A is said to be reflexive if A comma A belongs to R for every A inside A. Okay, right. So the empty relation is a trivially reflexive relation. Okay, so we don't consider the empty relations and all. Okay, so it's trivially reflexive because you cannot find an element A such that A comma A doesn't belong to R. Okay, because A is an empty set. So that is why we are not talking of relations on empty sets. Okay, so that's why I have defined it for a relation R on a non-empty set. Okay, so a relation R on a non-empty set A is to be reflexive if the ordered pair A comma A, that is A is related to itself. Okay, for every A inside A. Okay, so this part is important, that for every A. Okay, this should be related to itself for every A inside A. Okay. Under what condition a relation will be not reflexive? Okay, a relation is not reflexive if, I have already told you the opposite of or negation of this for every is there exists. So if there exists an element inside A such that A comma A isn't in R. Okay, so we may note it somewhere that a relation R on a non-empty set capital A is not reflexive if there exists an element A inside capital A such that A comma A doesn't belong to the given relation. Okay, if we can find such an element which is not related to itself, then we can conclude that it's not a reflexive relation. Okay, so say some examples of reflexive relations. For example, some examples of reflexive relations. Say A equal to the set 1, 2, 3. And you take R to be this set. So in reflexive relation, every element should be related to itself. Okay, other than that there can be any other element, no problem. Okay, so these three are A has 3 elements, so at least these 3 relations should be there. 1, 1, 2, 2, 3, 3. Okay. And other than that, you write something like 1 goes to 2. Okay. Okay. Even if you don't write, it's okay. Okay. So this is a reflexive relation. Okay. So this is reflexive. Okay. This is a reflexive relation. Then suppose I say R1 equal to something like 1, 1, then 2, 2, then 3, 3. Okay. Only this. This is also a reflexive relation. Okay. Every element of A is related to itself. Okay. This is also a reflexive relation. Say R2, I write something like 1, 1, 1, 2, then 1, 3. Okay. Then 2, 2, and 2, 3, 3. Okay. This is also a reflexive relation. Okay. But if I write something like R3 equal to the set say 1, 1, 1, 2, then 1, 3, okay, and then 2, 2. Okay, this is not a reflexive relation. This relation is not reflexive. Why? Because the element 3, which is in the set A, but 3 is not related to itself in the given relation. So R3 is not reflexive. Okay. 1, 1 is there, no problem. 2, 2 is there, no problem. But 3, 3 also has to be there. So R3 is not a reflexive relation. Okay. Okay. Next type of relation is symmetric relation. The second type of relation is a symmetric relation. You have done these things in higher secondary. Okay. So it's a sort of repetition. Symmetric relation. So a relation R on a non-empty set, is said to be symmetric. In a non-empty set, say capital A, is said to be symmetric if AB inside R always implies that BA is also inside R. Okay. If A comma B inside R, so for any given A comma B in capital A, the following is true. Okay, the following is true. Okay, so we can write it in a better way, this way. The following is true. Okay. So if you select any two arbitrary elements, if they are related, then the opposite has to be related. You order it in opposite way, that also has to be related. Okay, so a relation R on a non-empty set A is said to be symmetric if for any given AB in A, the following is true. AB belongs to R implies BA belongs to R. Okay, if AB belongs, then BA should belong to R. Okay, this should be true, right? So for example, if we take something like A equal to, say this set 1, 2, 3, and I take R to be 1 related to 2, 2 related to 1, okay, and then suppose I take 3 related to 3. So this is a symmetric relation. See, 1, 2 belongs to this relation, 2, 1 also belongs to this relation. Okay, 3, 3 belongs to this relation. You change the order, 3, 3. This also belongs to this relation. Okay, so this is a symmetric relation, right? Next, if we see something like this, R1 equal to, say, 2 is related to 3 and 3 is related to 2, 1 is related to 2 and 2 is related to 1. Okay, this is also a symmetric relation. This is a symmetric relation, right? 2 is related to 3, no problem. But we need, once 2 is related to 3 here, we have to check whether 3 is related to 2 or not. If that is not true, then it's not symmetric. So here 2 3 is related, so 3 2 is also related here. Okay, 1 2 is related and 2 1 is also related. So we can safely say that yes, it's a symmetric relation. Okay, so it's not necessary that 1 should be again related to 3. It's not necessary. Okay, if 1 is related to 3, then 3 should be related to 1. Okay, this condition should be satisfied. Okay, so this towards is symmetric. If I write something like this here, that R2 is equal to 1 related to 2 and 2 related to 3 and 3 related to 1. Okay, this is not symmetric. Okay, this is not symmetric. Why? Because here the 1 is related to 2 but 2 is not related to 1. Okay, here 2 is related to 3 but 3 is not related to 2. Okay, 3 is related to 1, 1 is not related to 3. Okay, even if one of them doesn't satisfy, then also it's not a symmetric relation. Okay, suppose I make it something like this. 1 related to 2, 2 related to 3, 3 related to 2. Okay, even then it's not symmetric because 1 is related to 2 but 2 is not related to 1. Okay, these two are okay, 2 3 related, 3 2 is related, that's fine. Okay, but for the relation to be symmetric, given any a and b in A, this should always be true, that if A and B belongs to R, then BA also should belong to R. Okay, and if A and B doesn't belong to R, then we don't have to worry about. Okay, but whenever AB belongs to R, BA also should belong to R. Okay, and that is the symmetric relation. Next type of relation that we have is transitive relation. Okay, transitive relation. Okay, so a relation R on a non-empty set, capital A, is said to be transitive if given any A, B, C inside capital A, the following is true. Okay, what is true? The following is true. A comma B belongs to AB and BC belongs to R implies AC should belong to R. Okay, right? If A and B are related and B and C are related, then A and C have to be related. Okay, if that happens for every A, B, C, okay, then this is said, the relation is said to be transitive relation. Okay, this implication should be true for any given A, B, C. Okay, means whenever A and B are related and B and C are related, then A and C should be related. Okay, it may happen that A and B are not related, so then in that case we don't have to worry about. Okay, but whenever A and B and B and C are related, then A and C have to be related. Okay, so for example, suppose A is the set 1 2 3, and you take R to be this 1 is related to 2, 2 is related to 1. Okay, so I have this type of structure now. A is related to B, B is related to C. I have constructed a relation where I want to construct a transitive relation. So the first two elements that I have taken is 1 related to 2 and 2 related to 1. So if I want this to be transitive, what should be the third element? The third element should be this one. 1 should be related to 1. Okay, then this relation will be a transitive relation. Okay, whenever AB and BC are in R, AC is also in R. Okay, so this is a transitive relation. Okay, this relation is transitive, right? I write something like R1 equal to, say, 1 related to 2, 2 related to 3. Okay, this is not going to be a transitive relation. This is not a transitive relation. Why? Not transitive. Not transitive. Why? Because 1 is related to 2, 2 is related to 3. If it has to be transitive, then 1 should also be related to 3. Okay, 1 3 should be an element. Okay, so here 1 3 is not an element. That means this R1 is not a transitive relation. Okay, it's not transitive, right? What about this? Can you say this is transitive or not? 1 related to 2, okay, 3 related to 1. Is it transitive, this relation? 1 related to 2, 3 related to 1 here. So for understanding this, we need to understand something more about this logic, mathematical logic. Okay, so what did I say? In the first class also I discussed a little bit about the mathematical logic. Okay, so a relation will be symmetric if given any A, B, C inside capital A, this implication is true. Okay, AB comma B, AB belongs to R implies BA belongs to R. Okay, this implication is true, right? So it's not symmetric. Under what condition we can say that a relation is not symmetric? The relation will be not symmetric. Sorry, here C is not required for the symmetric part. Okay, yeah. So under what condition can I say that a relation is not symmetric? So a relation will be not symmetric if we can find out some A and B inside A such that this implication is false. Okay, what is meant by implication is false? Implication is false means this is there, but BA is not there. Okay, BA does not belong to R. Okay, this means this. So a relation is symmetric if given any A and B inside A, this implication is true. The implication is true. What is the implication? Implication is whenever AB is in R, BA should be in R. Okay. So not symmetric if there exists some elements A and B inside A for which the implication is false. Okay. So the implication, these are the rules of mathematical logic. The implication P implies Q is false when the hypothesis is true but the conclusion is false. Okay. So here if AB belongs to R but BA doesn't belong to R. Okay. In that case we can say this doesn't imply this. Okay. So a relation is not symmetric if we are able to find out some elements A and B inside A which do not satisfy this particular condition. Okay. So yeah. So can I say that this R2 is not symmetric? Yes, we can say, because 1 2 belongs to R2 but 2 1 doesn't belong. Okay. So 1 and 2 are such elements which satisfy this. Okay. And under what condition a relation is transitive? A relation is transitive if I write it in terms of these things, mathematical logic, if given any ABC inside A, this is true. Okay, the implication is true. AB, BC, if AB and BC are in R, then AC should be in R. Okay, AC should belong to R. Okay, if this implication is true, then it's transitive. So under what condition can I say that a relation is not transitive? No, not transitive. Can I say if I want to say that a relation R is not transitive, then I have to find some elements A, B, C inside A for which this is not true. So I have to find some elements A, B, C inside A for which A, B and B, C they belong to R. Okay, they belong to R, but AC doesn't belong to R. Okay, AC doesn't belong to R. Okay, if I can find such elements, then I can conclude that the relation is not transitive. Okay, now let us come to this particular relation 1 2 3 1. I have asked that whether this is transitive or not. Okay, is this a transitive relation or not? Is this relation transitive? Okay, so you see 1 2 is there, so immediately we will look for 2 1. Okay, but that's not necessary. Okay, see, if I want to say that this is not transitive, then I have to find some elements A, B and C such that AB and BC are in the relation, but AC is not there in the relation. So can you find such elements here? Say 1 2, 1 2 is there, but nothing is there with 2 related to something that is not there. 3 1 is there, but nothing is there with 1 3. Oh yeah, sorry, 3 1 is there, and something is there with 1 2. So 3 1 is there, 1 2 is there, okay, but 3 2 is not there. Okay, so this relation is not transitive. Okay, so immediately we can say it's not transitive because we have been able to find 3 elements. What are those elements? 3 1 and 2. Okay, 3 1 is there, 1 2 is there, but 3 2 is not there. Okay, so this is not transitive. Okay, now let us consider another one. This relation, say on the same set, say I take this relation, say 1 is related to 2, and yeah, just 1 is related to 2. Is this a transitive relation? Is this relation transitive? So here 1 is related to 2, so immediately we'll think that there is nothing with 2 related to something else. Okay, so here can we say that it's transitive, or rather can we say that it's not transitive? If I want to argue that it's not transitive, then what I have to do? I have to find elements, say A, B and C, such that AB and BC, they are inside this relation, but AC is not there inside relation. So can you find such an element, such 3 elements? Can we find? We cannot find, because this set, the ordered pairs are, there are only 2 elements in one of the ordered pair. Okay, so I cannot find something like 1 2 2 3 such that 1 and 2 are related, 2 and 3 is not related, but 1 and 3 are not related. Okay, so we cannot find such a ABC. Okay, the relation will be not transitive if there exists some ABC inside A which do not satisfy this. So here for this relation we cannot find such ABC inside A. Okay, there are only 2 elements here. We will never find such ABC which do not satisfy. Okay, so we cannot justify that it's not transitive. We have to agree that it's transitive. Okay, so this is a transitive relation. Okay. Okay, so suppose another one, I take something like 1 2 and 3 3. Okay, now also it's a transitive relation. This relation is also transitive. Okay, you cannot find some elements like A B C where AB and BC are inside R. So see, 1 2 is there, 3 3 is there, nothing with 2 and something else. Okay, so you cannot find elements like see 3 3 is there, and again 3 3 is there. So for that 3 3 is already there. Okay, so we for this element 3 3, everything is satisfied. 3 3 and 3 3, they belong to the same relation. It implies 3 3 belongs to the same relation. We are talking about the same element only. Okay, so here this relation is transitive. We cannot find such ABC which for which AB and BC are in R, but AC is not in R. Okay, so this relation is transitive relation. Clear? So these are the symmetric relation, reflexive, transitive. Okay, so let us try some more examples or exercises. Give example of a relation that is reflexive and say reflexive and transitive. Okay, it is reflexive also, transitive also. Okay, reflexive, transitive, but not symmetric. Okay, but not symmetric. Can we give some example of that relation? Okay, so obviously with 1 2 3 4 we can construct. So let us go to some other standard examples. Okay, give example of a relation that is reflexive, transitive, but not symmetric. Okay, so first of all, to construct a relation we need to fix a set, that is the universal set we have to fix. Okay, So let Z be the set of integers. Okay, set of integers. Okay, so we construct a relation R on Z as A comma B belongs to R if and only if A is less than or equal to B. Okay, so we could have started with the set of real numbers also. Okay, say if and only if A is less than or equal to B. Okay, AB is inside R. So given any A comma B belongs to Z. Okay, so A and B are elements inside Z. AB belongs to R. AB will belong to the relation if and only if A is less than or equal to B. So this is a symmetric relation. Why? To prove that it's symmetric, let us start with an arbitrary element. Let A belongs to Z, be any element. Okay, be any element. Okay, then what we can say? A is always equal to A. Okay, A is always equal to A. So this holds. Okay, this holds. A is less than or equal to B. Okay, whenever A is less than or equal to B, AB will be inside R. So if A belongs to Z is any element, then A is always equal to A. So therefore, by definition, by definition of the relation, by definition we can say A comma A belongs to R. Okay, A comma A belongs to R. Okay, and since A is an arbitrary element, so we can write A comma A belongs to R for every A inside Z. Okay, so it's reflexive. For reflexive, we want that every element should be related to itself. Okay, next, whether it is transitive or not. So for transitive, we have to take 3 elements. Let A, B, C belongs to Z. Okay, such that we have to take 3 elements such that A and B are related. Okay, A, B, B, C, they belong to the relation. Okay, so what does this mean? A, B belongs to the relation means A less than or equal to B, and B, C related means B is less than or equal to C. So this will imply that A is less than B, B is less than C. This will always imply that A is less than or equal to C. Okay, so we can say A and C are related. So if we start with any 3 arbitrary elements of Z which satisfy A, B and B, C belongs to R, we also get the can conclude that AC belongs to R. Okay, so that means this is a transitive relation. Okay, so the relation is transitive. Okay, but this relation is not symmetric. Why? This relation is not symmetric. Why? So it's not symmetric. Why? So we have to find 2 elements AB inside Z which satisfy A less than or equal to B, but they do not satisfy the other way around, B less than or equal to A. Okay, so not symmetric. Why? So it's very easy to find out. 1, 2, it belongs to R. Why it belongs? As 1 is less than 2. Okay, but we cannot say that 2, 1 belongs to R. So 2, 1 doesn't belong to R because 2 is not less than 1, right? So 2, 1 cannot belong to R. Okay, so the element 1, 2 belongs to R, but 2, 1 doesn't belong to R. So it's not symmetric. Okay, it's sufficient to give one example. Okay, to show that it's not symmetric. Okay, because if it is symmetric, then for every element of the form AB in R, the element BA also, the ordered pair BA also should be inside R. Okay, so if we are able to get at least one element for which AB is in R but BA is not in R, we can always conclude that the relation is not symmetric. Okay, so this is the example of a relation which is reflexive, transitive, but not symmetric. Okay, so I'll give you some more exercises. You try these things. Given say for this one. So the first one already we have seen, reflexive, transitive, but not symmetric. Okay, so first one is this. Second example, you try to do it yourself. reflexive, symmetric, but not transitive. Okay, reflexive, symmetric, but not transitive. Number 3, say it is symmetric, transitive. Symmetric is there, transitive is there, but not reflexive. Okay. And then number 4, say it's reflexive, it's not neither symmetric, neither transitive nor symmetric. Okay, it is reflexive but neither transitive nor symmetric. Another one is, say it's transitive, okay, but neither reflexive nor symmetric. Okay. Number 6, say it's symmetric but neither transitive nor reflexive. Okay, so you try these examples. Okay, these are very important. Okay, these things were done in your higher secondary also, still you try to recall. Okay, so in the next lecture we'll see some more examples of these things.